In this lesson, we're going to go over an introduction into graphing quadratic functions. Before we actually graph these functions, let's talk about the main ideas of quadratic functions. So the definition of a quadratic function is that it has to have the highest exponent of 2. So when you have an exponent of 1, that's a linear function, and we looked at those before. Now when your exponent is a 2, that is called a quadratic, and it can have up to 3 terms in it. When you graph a quadratic, the graph looks like this. This is a parabola. It's a U shape, and that U shape can either face upward or downward, and it can have different steepnesses. The uses of quadratics in real-world problems have to do with finding area of spaces, determining the profit of a business, and predicting the speed and height of objects in sports, just to name a few. So we're going to spend another day all on graphing exactly and looking at applications in detail. Today is just kind of an overview and an introduction into this concept. A few things to note about quadratics. So like I said in the graphing part of the last slide, the graph of a quadratic, which is called a parabola, can either open up or down. So in this case, this one on the left, we can see that this one opens up. And when it opens up, the vertex is going to be a minimum point. So this has a minimum. On this other parabola here, this parabola opens down, and this vertex is going to be a maximum. And we can tell, besides looking at the actual graph, whether it opens up or down, based off of the equation, we're going to focus on the a value. And we're going to talk more about this in the next slide, but for now, I'm going to say that the a value is positive if the graph opens up. So that way, by looking at just an equation, we can figure out if the graph will open up or down. If the a value is negative, then the graph will open down. So the way I like to think about it is if you're a positive person, you smile. So if a is positive, it's going to open up like a happy face. If you're a negative person, you're going to frown. So if a is a negative value, your parabola will be pointing down. Another thing to make note of is the fact that parabolas are symmetric. So if we were to draw an imaginary line right through this parabola going through this vertex point, and we were to fold this parabola on top of each other, they would match up perfectly. So this idea of being symmetric is going to help us when we're starting to graph these quadratics. This imaginary line that we draw is called the axis of symmetry, and it's cutting right through that vertex point. So we're going to come back to all of these when we look at the examples. Now, quadratics can really be written in 3 forms. We're only going to look at 2 of them today. So the first form we're going to look at is vertex form. So vertex form, this is your general equation for vertex form. F of x equals a x minus h squared plus k. Now, vertex form is actually very easy to find the vertex. That's why it's called vertex form. The vertex in vertex form will always be h comma k. Notice what's inside. We have x minus h, so it will always be the opposite of the value that's inside, so the opposite sign, and then exactly what's outside. We can think about this with transformations that we talked about in the first unit. If we know a parent function of a quadratic is x squared, we can tell that minus h means it's moving horizontally, and the plus k means it's moving vertically. So let's think about this when we look at this first example. So f of x equals negative x minus 5 squared plus 1. So this is in vertex form. If we were thinking about transformations from the first unit, we could see that this negative in front means that it's a reflection over the x-axis. We can tell that this minus 5 is moving to the right 5, and this plus 1 is going up 1. So the parent function of x squared would have its vertex at 0, 0, but because we're moving it right 5 and up 1, our vertex will move to the right 5 and up 1. So our point for our vertex will be 5, 1. So we can think about that in terms of the transformations, or just the fact that it's the opposite value of what's inside. So we see a negative 5, so the x value of the vertex will be positive 5. And then the y value of the vertex is the number that's added or subtracted outside of the parentheses. So that is 1. Okay, so without doing any math, we just looked at the equation and we could figure out what the vertex is. On this table of values here, we're going to put the vertex in the middle. So 5 is the x, 1 is the y. In order to graph a parabola, you need at least 3 points. So we're going to do 5 points. The idea that a parabola is symmetric is going to help us here, because if I pick points on either side of the vertex, as long as they're the same distance away from the vertex, the y values will be the same. So if I pick 4 and 3, and 6 and 7. Now 4 is the same distance from 5 as 6 is from 5. So the y values at 4 and 6 will be the same. In order to find the y values, we're just going to plug them into this function. So I'm just going to pick 4. So if I plug in 4, I'm going to have negative 4 minus 5 squared plus 1. When we're doing this, we want to make sure that we're careful because we want to make sure that we use the order of operations. So we're going to do 4 minus 5 first, which is negative 1 squared plus 1. So we're going to square the negative 1, which is positive 1. But then we have this negative on the outside, and then this plus 1. Negative 1 plus 1, well, that's going to give us 0. So the y value will be 0. If we plugged in 6, we would also get 0, so you can double check by plugging it in, or just know that it's symmetric, so it will have the same y value. Okay, and then we would do the same exact thing for 3. We would plug 3 in for x. If we do that, we will get negative 3. Let me change colors here. That will give us negative 3. And then if I plug in 7, because it's the same distance away from the vertex as 3 was, it's going to have the same y value. So when we go to plot this, we have a parabola that will open down. So we can see that it opens down based off of how we're graphing it, but also the a value. The a value is negative. So when you're negative, you have a frowny face. So it's going to point down. So here's our graph. To find the y-intercept, we need to plug in 0 for x. Plug 0 for x. So if I plug in 0 for x into this function, okay, we're going to get negative 0 minus 5 squared plus 1. So 0 minus 5 is going to give us negative 5 squared plus 1. Negative 5 squared is 25. The negative stays in front because that is a negative 1 in the front of everything. Negative 25 plus 1 is going to give us negative 24. So for the y-intercept, the x is 0 and the y value is negative 24. After this, all of the math is really done. The axis of symmetry is going to be the imaginary vertical line that we draw right through the vertex, and that will always be written as x equals, because it's a vertical line, and will always be x equals the x value of the vertex. So the x value of the vertex here is 5, so x equals 5 will be our axis of symmetry. Okay, since this parabola opens down, it means it will have a maximum value, and the value it has a maximum at will always be the y value of the vertex. So a max value at 1. Okay, and then the domain and the range, we should know this from the functions unit that we had where we did domain and range. Domain is the x values, so if this continues forever, the x's will be going all the way left and all the way right. You can choose to write this in either set builder notation or in interval notation. I'm going to write it in interval notation. So we will say that the domain is from negative infinity to positive infinity. The range is the y values, so we want to go from the lowest y to the highest y. Since they're going down forever, these arrows, that means that the lowest y will be negative infinity. The highest y is going to be the y value of the vertex, which is 1, and we'll have a bracket. Okay, so once we find the vertex, the axis of symmetry, the min and max, and the range are all coming from the values of that vertex point. Okay, so let's look at another example of vertex form. So again, if we're thinking about transformations, we can see that this 2 in front, this means that we have a vertical stretch of 2. We can see that this plus 6 means that we're going to the left 6, and this minus 3 means we're going down 3. So if our vertex was at 0, 0, and we went left 6 and down 3, our vertex would be negative 6, negative 3. Again, it's just the opposite, of what's inside and exactly what's outside. Since we know negative 6, negative 3 is our vertex, we'll put that in the middle. And then we're going to pick x's that are on each side of this vertex point. So I'm going to pick negative 7 and negative 8, and then negative 5 and negative 4. Again, we're going to plug them into this equation for x. So I'll just do the first one really quick. If we plug in, let's say negative 7, I have 2 times negative 7 plus 6 squared minus 3. Negative 7 minus 6 is going to be negative 1. I will square that. Negative 1 squared is going to be 1. 2 times 1 is 2. Minus 3 gives us negative 1. So when I have an x of negative 7, y is negative 1. Because it's symmetric, I know negative 5 will also have a y value of negative 1. If I plug in negative 8 into this and we solve it, we will get 5. Because it's symmetric, negative 4 will also give us 5. So we can go ahead and we can plot this. So we can see that based off of just the equation, we can see that the a value is positive, so we know that this is going to open up, and as we're graphing this, we can see that it indeed opens up. So, ooh, that is not even good. So let's pretend like we could draw this properly. Ooh. Oh boy, let's just pretend that I drew this correctly. Okay, so that's done. Y-intercept, we're going to plug in 0 for the x. So when we plug in 0, remember to follow the order of operations. 0 plus 6 is 6. 6 squared is 36. Times 2 is 72. Minus 3 is 69. So 0, 69 will be our y-intercept. Now that we have the vertex, we can find the axis of symmetry. That's x equals the x value, so negative 6. We can see that this parabola opens up. The a value is also positive, telling us that it opens up. So we have a minimum here, and the minimum value will be at the y value of the vertex, so negative 3. And then the domain is going to be the same for every single quadratic that we do. So your domain will be negative infinity, comma infinity. And the range, we're going from the lowest y value, which is the y value of the vertex, so bracket negative 3, to the highest y value. Since there's arrows going up, it will go to infinity. So that is our range.